I would like to welcome into this fantastic moment. And I would like to take this opportunity also to greet, how are you, wherever you are. My name is Olenjolaim Singo from beautiful, fantastic country called United Republic of Tanzania. And this is our national flag that we used to use this one as just our unique identifications. So I would like to welcome you into these fantastic sessions. And first of all, I would like to welcome you into my official YouTube channel called Tanzania Online A-Level Secondary Schools, in square bracket Olenjolaim. The main visions of this channel is solving the problems which are existing that happens. Many students, they fail to understand different concepts in advanced physics, advanced chemistry, and advanced mathematics, and also in basic applied mathematics. So the contents of this channel, so in these channels we'll be teaching or we'll be solving those problems that are existing to the students and even teachers who are teaching these subjects. So that's the main visions and the main goals of this channel, YouTube channel. And also we have 3 departments in these online schools, or online A-level secondary schools. We have departments of mathematics, departments of physics, departments of chemistry. So now we are in departments of advanced physics, and the subject we are going to learn is advanced physics. The main topic is mechanics, and then the topic is gravitation. And this material is for the Form 5 or Pre-Form 5, Form 6, and also ordinary diploma students. That's the little introductions concerning about departments and even the video. So today I'm going to teach you lecture or period or sessions 9, which is very fantastic sessions. We'll be having problem solving. So the topic, so we'll be having, first of all, I'll be teaching you about escape velocity as the corrections of the homework. Escape velocity are the corrections of the homework. I left it in as homework 8. Okay, so because it's very important, I'll be teaching this escape velocity, solving one problems, and then see what will be next, because we have a lot of things to cover. So I would like to ask you that to subscribe, because we'll be uploading many videos in this channel, and also that I would like to ask you to share this material with some other colleagues. And in case that you want to ask questions, use the comment sections to ask your questions as well as you can, and I will try my level best to answer. And even some other students in the world, in America, in Africa, in Tanzania, or in different regions of Tanzania, in Asia, in Australia, and even in America, they can answer your questions, because you know that when advanced physics is kind of universal. So in different institutions or different countries, they used to learn that concepts of advanced physics. Okay, so again, I remember that this is a channel for the serious students. So if you're not serious, this is not a comfortable place, unless you want to be transformed from being unserious to be a serious student. So take all the required materials for learning for the serious students, and then let us go to the session at this moment. I believe that you did the homework that I left in sessions or lecture or period 9. And so very fantastic homework, I think, for you, because you know that you don't like these materials. Maybe you have defined what the mix of escape velocity, and then you ended there. But that's not the end. Escape velocity contains a lot of things, and it's a very important concept in gravitational mechanics. So if you don't take it, it means you don't pay attention, and even the homework that I gave you should understand what the means of escape velocity. You should also understand where we apply the concepts of escape velocity, why do we need it, and then what are the mathematical formulas which can help the astronomers or maybe the spacecraft specialists to do the computations of escape velocity of particular satellites, or maybe any planetary or any heavenly body that has been sent to the particular place. Okay, so whether you did, if you did, congratulations, let us do minor correction. And if you didn't do, I'm very sorry. I'm very sorry, and I'm happy to see students who are lazy and who they don't do the homework. So simply, before I start these concepts of the escape velocity, I would like just to do the quick review of what we covered in lecture 8. So in lecture 8, we have covered many concepts, but I would like just to quickly review a few of them. I taught you about gravitational, the concepts we call the gravitational field, right? I taught about gravitational field. And as I taught you another concept that we call the gravitational field strength, and this is the vector quantity. Again, I told you about the work done required to bring what? Work done required to bring the satellites from the infinity, maybe or a body, to bring a body from infinity to the point, means to R. Hence, I told you again about gravitational potential, which is V. I told you about gravitational potential energy, which is U. I told you about the potential energy, which is U, as I say. And as I told you about kinetic energy, and I told you about the total energy, and I told you that the relationship between kinetic energy and the gravitational potential energy. So we discussed a lot, and I left the homework for you. So one of the longest lecture or session in gravitational from the beginnings to the point where we are. So today, let us navigate in these concepts of 40 of escape velocity, and the fundamental questions we have to ask ourselves is, what is escape velocity? So say escape velocity first, okay? Get prepared to enjoy the beauty of physics. So what is escape velocity in gravitation? That's the fundamental question. Think, if you did the homework, without watching what you found or what you have written, try to use the knowledge you have got when you have been doing your private study. How can you define escape velocity? What is escape velocity? Right? Okay. So I think you have get the response, whether you remember or you left the sentence or the definitions in the exercise book. It happens for A level. Okay, so I found number of almost more than one definitions of escape velocity, and I would like to share with you. So you say the escape velocity. So what is escape velocity? You say that the escape velocity of a body, you say that is a minimum velocity. So this is the minimum. So this is minimum velocity. This is minimum velocity with which it is to be projected. So this is the minimum velocity that required to project or projected in, so that be projected so that it just overcomes the body, just overcomes what? The gravitational pull. The gravitational pull. This is the definition from the principle of physics by S. Chandler, class 11, of the S. Or any other planet. Or any other planet. So this is the one of definition. Okay? So again, when I visited it as a reference books, I found some as a definition of escape velocity. Why am I giving you several definitions? Because I want you to understand the term that we are learning or we are discussing at the time. Okay? So some of the references, so this is the reference is principle, as we call it S. Chandler. S. Chandler's principle of physics. Principle of physics. And this is page 700. Page 703. 703. So some other references also define that escape velocity is a minimum velocity or initial velocity, the minimum initial velocity, which given, or minimum initial velocity, so it's a minimum initial velocity required by a body, for example, a satellite or some other bodies, heavenly bodies, okay, so as to be removed, completely from the Earth's gravitational field. So let me explain what are written on the blackboard. Our aim, we want to define the terms and understand clearly the terms called the escape velocity. So escape velocity, we say that of a body is a minimum velocity according to the principle of physics, with which it is to be projected, so this body to be projected, so that it just overcomes, what the gravitational pull of the Earth or any other planet. So these are the keywords that I have underlined. So is this the minimum velocity that required by a body to be projected from the maybe Earth's surface, or from Earth's surface or from a certain planet, so that it overcomes the gravitational pulls, because there's a gravitational pulls of the Earth provided to the any body that within the gravitational field of the Earth. Not only the Earth providing the gravitational pulls, even some other satellites, some other planets provides also the gravitational pulls. For example, Jupiter also provides gravitational pulls to anybody, and we computed its gravitational acceleration gravity or gravitational pull is how much. And we found that it's a little bit different from the gravitational pulls of the Earth. Again, for example, if you send maybe a body is in the surface of the moon, also the moon, there are gravitational pulls existing in the moon's surface. So what do you say that? So this is the definition. Or in some of the references we say that escape velocity is a minimum initial velocity. Is a minimum initial velocity required by a body so as to be removed completely. Right? To be removed completely from where? From the Earth's gravitational field. This is very fantastic and useful definition. So this is the minimum velocity. It's not maximum velocity, it's not medium velocity, that's number one. And also this is not a final velocity, it's initial velocity. Right? So you should know that this is the minimum velocity of the body of the satellites, for instance. And also this is the initial velocity. It's not final, it's not intermediate velocity, it's not average velocity. It's initial velocity of the body. And this velocity is required when we want to send a body away from the Earth's gravitational field or from the Earth's surface. That's the point when we need the escape velocity. So escape velocity, this is the velocity that when, for example, myself as a teacher, I will be given the escape velocity, the minimum initial escape velocity, or the minimum initial velocity, which is called the escape velocity, then I will be leaving or be removed completely from the Earth's surface. So that's what we say, that we send the body outside of the space. Okay, so outside of the space, it means that that body will not be disturbed or challenged by the gravitational pulse of the Earth. So that's the meanings of escape velocity. Remember, there's a difference between escape velocity and the orbital velocity. These are the two different terms. You have to remember them in your mind. So that is the definitions of escape velocity. Well, so this is a little bit interesting velocity, because we say that since the S's gravitational field extends to infinity, however weak it may be a large distance, or large distances, escape velocity is obviously the velocity that must be given to the object for it is escape all the way to the infinity. So when you say infinity, it means the regions where there is no gravitational field or gravitational force. So you say that anybody, when you say anybody, for example, you say that satellites, or we call it, or for example, space vehicles. Okay, so anybody or space vehicles, anybody that is projected we are maybe from the Earth's surface, or other planet surface, but we say that from the Earth's surface because that's the manufacturing center. From the Earth's surface, with the escape velocity, with escape velocity, So with escape velocity, we say that in space, satellites or space vehicles that is projected from the Earth's surface with escape velocity, it will be completely removed, okay, from the Earth's surface to the infinity. So simply we say that escape velocity, this is the minimum velocity that, so escape velocity we say that is a velocity that takes the body from the Earth's surface where there is a gravitational force, the Earth's surface to the infinity. So when you say to the infinity, it means this. Okay? So that's the basic concepts of escape velocity. So we are discussing about taking a body from the Earth's surface to the infinity. That's very important point. So after I've introduced it to you, the meanings of the escape velocity and what does it do, and I gave you more than what you found, because I know that at this stage you might be very lazy because you don't know how A-level or advanced life is expensive. In case of hard working, then possibly you just define and then you say it's ready. So I'm ready to show up. If Olenjolaim is there, I can show that I am done with the homework of escape velocity. But you are really joking. Okay, so he said that now I would like just to teach you the derivation of the general formula of 14 of determining the escape velocity of anybody. So I want to teach you the derivations, the steps. We have to follow several steps. The first step, we say that consider the body of mass m. Consider the body of mass m You can use the comment sections to ask many of your questions as well as you can. Consider the body of mass M that revolves or that gained, or which gained the escape velocity. Escape velocity to what? To infinity. So we say that this is the concept. We have the S surface. We have the center of the S surface like this. We have mass of the S. Or even here you can write mass of the S. And then we have the S surface. We have the S surface like this. So this we call it the S surface. S surface. Or the S gravitational force, that's what we call. Okay, so I think that, yes, let me draw it clearly. Suppose that this is the S surface, the entire S surface, which is circular. Then this is the center. Here you have mass of 40, mass of the S. So you say that suppose that this is the S surface, S surface, and then this is the point, right? So at this point, this suppose that is point A. The distance between the center of the point A and the center of the S is called the radius of the S. So that the distance from point O, let's say, to point A. Then now, at this point, we want to give the escape velocity to the body, that is at the distance r e from the S surface. And then we give its initial velocity, and it will be removed to 30 to the infinity. So suppose that this is the point where we have our body of mass M. So body of mass M. So this is point B. So if it's point B, then we say that we have what? The distance. Right? Have the distance. Have the distance, and this distance from what? From the center of the S, from the center of the S to the point or to the infinity region. So this distance, we call it x. So the distance is what? Is x. Again, we say that because this is the amount of work done that required to remove a body from point A, where the gravitational force is acting. Listen carefully. There's a work done required to remove a satellite or a body from point A to point B. And that work done, remember that we may take even consideration that because the distance from here to here is x. So suppose that we want to know the amounts of work done which has been done between point A and point C. So if that's the case, we have a small distance here which has been traveled by a body of mass M. So this is the body of mass M. And this small distance, we call it dx, or in other words, we call it change in x. Fantastic. So that's a concept that you have to remember, and that the real presentations of 40 of the escape velocity. So that is the S surface, then this is the body, and then here outside we call it outside, or we say that no gravitational field. So we say that out of the space. So this is out of 40 of the space. So out of the space means G does not act on anybody that outside of the S surface. That's the meaning. So if that the case now, we have our circular orbits like this, because circular S is surface. So remember that this body, when it reaches the infinity, it will be revolving possibly the S in its particular orbit, like this, right? But it's free from gravitational pull. That's the concept that you should remember. So then we go for the second step. The second step that we say we have to remember how we get the small amounts of work done. We say that from the formula of work done, okay, is given as work done is equal to force times distance. I believe that you remember in the previous lecture, social lecture 8, we discussed about that. Work done is equal to force times 30 times distance. So from this concept, or from the force, or from Newton's universal law, or universal gravitational, we say that the force of attraction between the body and the S will be the product of gravitational constant as mass of gravity of the body as mass of the S over r squared. The radius for this case is the distance from the center of the S to the point B. So this is gravitational constant, mass of the body is mass of the S of what? Radius for this case is xc squared. Xc squared. So that the force of attractions between the S and the body of mass M. So remember our formula that we say that work done is equal to force times distance. This is the meaning of the distance. So if that the case now, we say that the force of attractions is equal to gravitational constant mass 1 mass of the S over x squared. Suppose that this is the first equation. Again, we say that in this the third step, we say that small change in amount of work done will be is equal to amount of force multiplied by small change in amount of the distance, which is x. So if you want to find the minimum amount of work done, that is, remove the body from the S surface here at the end of the S gravitational poles to point C. So the amounts of work done that will be done, or will be done maybe by using a rocket, so because the rocket is the one that is carrying the bodies to the outside of the space. So when it has been carried, it means that we say the amount of work that from point A to point C is equal to force times small distance, which is changing the x. So remember that when these 2 points are very close, because in integration we don't need to deal with this entire chunk. We just take a piece of it, derive the formula, and then we integrate. Okay? So this is the small amounts of 40 of work done. So I mean that we can think like the work done is equal to the work done is equal to force times 30 dx. So I just think the notations of derivative. This is change and this is change. So we say again that D, so suppose that this is the second equation. So either the second equation say that we have the first equation, or we say that let us take equation 1, take equation 1, and then she said that we substitute in what? in question 2. What does it mean? We say that small change in work done is equal to force, which is equal to rotational constant, mass of the body, mass of the S, over x squared, z times 30 times dx. Right? So great. So if that's the case, this is the same equation. Continue the first step. So the first step now, we say that integrate equation 3, which determines the s-square velocity, equation 3. Integrate equation 3 to both sides. That's why we told you have to learn calculus first. Both sides. Okay, so if that's the case, we have the work done. As of the S, then have x squared dx. So now remember that we are looking for the work done that required to remove a body from the S surface to outside of the S surface. That's what we are dealing with. So we say that today we integrate it from radius of the S, which is RE, to infinity. So remember that in the work done of bringing an object or a body from the infinity to the radius r, we integrated it from infinity to r. So even here that we say we integrate from 0 to work done. So if you integrate just for the simple simplification of this d and this integral sign cancel, on left hand side remains is what work done. So work done. So remember that all these numerator are constant. So gravitational constant is constant. Mass of the body m times mass of the s, and this one is constant. The remaining is what integral radius of the s to infinity, and then say what dx over x squared. So if that's the case, on left hand side we have work done is equal to gravitational potential, mass of the satellite, mass of the body, and mass of the s, and then we integrate from r, radius of the s, to infinity, dx over x squared. So to integrate that expression is very, very simple. Gravitational constant times mass 1 or mass of the body, that mass of the s. The way we integrate that, this x squared should be a numerator. So it means that we say that we integrate from RE to infinity. Listen careful, x power negative 2 dx. Right? Be careful, please. So work done is equal to gravitational potential times what? Mass of the body, that's mass of the s, if we integrate this, we can use power rule. x, or negative 2 plus 1, or negative 2 plus 1. From radius of the s to infinity. So the work done is equal to universal gravitational constant, mass of the body, mass of the s, and then square bracket